Okay, welcome to the section 2.1 pre-class video assignment. Today, we're going to start talking about solving higher order, specifically for the next few sections, second order differential equations. So these would be things that look like this. This would be the Leibniz version of it. This is something of a standard form, second derivative plus some function of x only times dy dx plus some function of x only times y equals f of x. So we're talking about, again, linear second order. So linear is what means that p, the function p here, can be a function of x only. If this has y's in it, then multiplying a function with y's in it times dy dx would not be linear. And again, the prime notation is probably a bit more succinct and commonly written here. Would look like that. So basically, we have a little terminology here. If the function on the right-hand side, the f of x function here, sometimes called the forcing function, which we will see why that is named that way later in the course. If this is equal to 0, then this is said to be a homogeneous differential equation or homogeneous differential equation. I think I use both terms interchangeably by accident. If the function is not equal to 0, then this is non-homogeneous. I've also kind of adopted my own notation here. For a homogeneous differential equation, I can write HEQ for short, and for a non-homogeneous, I write NHEQ for short. So we'll probably see that in the course, but that's probably my own personal notation. All right, so a little big picture stuff before we get too far here. Generally, homogeneous DEs are typically much easier to solve. So DEs where we have equals 0 instead of a function on the right-hand side, these are typically easier to solve. If you were to solve a non-homogeneous DE, typically we must first solve the related homogeneous DE anyway. So the first thing is a little bit of a terminology here. I'm using this term associated homogeneous DE to a non-homogeneous DE. Hopefully that's fairly self-explanatory. So for example, if we were looking at this guy here and this f of x was not 0, then taking that f of x off there and making it a 0 instead would be the associated homogeneous DE. So when we have y double prime plus p of x y prime plus q of x y equals 0, that would be the associated homogeneous DE to this guy if f of x were not 0. So here's a little fairly easy, second one is a bit of a trick question, but a bit of a MyOpen Math question on that terminology. All right, so we are going to concentrate first on how to solve homogeneous second order DEs. So homogeneous is equals 0. So we're going to spend a couple of sections on that. We are actually not going to solve them in this section. We're just going to cover some of the basics in this section, and we will see a method of solution a little bit later. One thing to note, you may have noticed that the constant function y equals 0 is always a solution to a homogeneous DE like this. That is not a very interesting solution. That we would call this the non-trivial solution. Excuse me, we call that the trivial solution. We are interested in finding non-trivial solutions. All right, so we're going to talk a little bit about the principles here. The first thing here is, what is the nature of the solution to a second order homogeneous equation, an HEQ? We will not formally solve these again in this section, but again, we're just looking at some of the principles. The first principle is something called the superposition principle for homogeneous equations. Superposition is a fancy way of saying addition. This is an addition principle for solutions to homogeneous equations. It basically says that if you have non-trivial solutions, y1 and y2, then any linear combination of them is also a solution. So if you have y1 and y2, and you know those are solutions to some differential second order linear homogeneous differential equation, then making a linear combination out of them, C1 plus, so C1 Y1 plus C2 Y2, where the C1 and the C2 is just any old constant, then this would also have to be a solution. So looking ahead a little bit, this should make some sense. If we have a second order HEQ, you can imagine solving takes integration. If this is second order, it's kind of like, oh, maybe this takes integrating twice. Therefore, there should be two constants of integration generated. So this is promising. This is an expression that contains two constants and is a solution like this. So this is actually kind of a preview of a general solution to such an equation. So here's a little proof of it. I will let you read it. It's actually pretty straightforward. Assuming that y1 and y2 are solutions, if y1 and y2 are solutions, it means if you plug them into a general differential equation, homogeneous, like this guy here, if this is your homogeneous equation, if you plug them in, it means you get 0 when you're done. If you substitute them in and evaluate, you would get 0. So this is true for y1 and y2. If you then take y1, if you then take our new function y, which is a linear combination of y1 and y2, the first derivative is just this, the second derivative is just this. If we plug this into our original DE, we are asking ourselves, the theorem states that this must be 0, so we can check it. But again, all we need to do is do some distributing and do some rearranging of the terms, and we get basically C1 times this guy here. This guy is just the DE with Y1 stuck inside it. We know that that is equal to 0. This guy here is C2 times the DE with Y2 stuck inside it. We know that this one is equal to 0. So we get C1 times 0 plus C2 times 0 is 0. So yes, plugging in, substituting in the linear combination C1Y1 plus C2Y2 into the DE would have to be a solution as well. So this is quite general. It means that, yes, plugging in y1 is a solution. Plugging in y2 is a solution. Plugging in 3y1 is a solution. Plugging in 17y2 is a solution. Plugging in 15y1 minus 37y2 would also have to be a solution. So this is what this theorem says. All right, so based on this, there's a little MyOpen math question. It's basically a true or a multiple choice, select all that apply, a bit of a thinking question. Give that a go here. All right, so next up, a little demonstration. So here's a demonstration with an actual example for the D. So here's a second order HEQ. Y double prime minus 8y prime plus 16y equals 0. The question is really just to verify that these two functions are in fact solutions. One of them is e to the 4x. The other one, y2, is x e to the 4x. So we are to verify that both of these things are solutions. Now, I have given you here, if you care to read through it, I have given you here how to check it by hand. We already know this. We can just find the appropriate derivatives, substitute everything in, and check to see whether we get an identity or not. What I would like to show you is a way to check this on the calculator. It's probably not necessary for an example like this, but I do want to show you this little trick on the calculator. I find this super helpful. I hope you find it helpful as well. Like if I've done a homework problem, I'm not sure if I got it right, I'm not sure if I have the right solution, I can use this little check to see if I have a solution or not. So let me go over to, I have something of a calculator simulator on here. It is a little squirrely, I must admit. So this is a little tricky for me. to do, but we're going to double check these questions. So the question was y double prime minus 8y prime plus 16 equals 0. Let me just double check. I already forgot. So plus 16y equals 0, and the functions were e to the 4x and x e to the 4x that we were checking. So let's go ahead and try that here. All right, so this is what I would do to check this. I am going to start out by, putting in, hold on, into my y equals button. So you go to this green star button, y equals. I am going to put into y1, let's put in the first function that I want to check, which is e to the x, e to the 4x, excuse me. So we're going to put that guy in there. So that's going to be y1. I know that's defined on my calculator as y1. Actually, why don't I do this as a little trick here? I'm going to also put in x times e to the, where's my e to the 4x into y2 as well. So these are the two functions I want to check. Then I'm going to go back to my home screen. And then in my home screen, I am going to plug in, I'm going to basically have the calculator evaluate the left-hand side of our DE. That is, I wanted to do second derivative. So second derivative on your calculator is second, and then we do the 8 key, that is derivative. Now I want to take the derivative. Let's start with y1. Now on the calculator, it doesn't know what y1 is. You have to put in y1 of x, y1 of x. And then I have to tell it that x is the variable here. That's like saying derivative with respect to x. And then if I put a comma 2 here, that will do a second derivative of y1. So that is my second derivative of y1. So what my DE says is do a second derivative of y1, then subtract 8 times the first derivative of y1. Again, if I'm doing first derivative, oops. Again, this is squirrely, like I said. I have been able to make it work in the past at times. So your calculator shouldn't act quite like this, hopefully. But here, first derivative of y1 is this, comma x, like that. So if I'm doing first derivative, I don't have to put comma 1. It will assume first derivative. And then the last thing I have to do is add, not multiply. I am adding a 16 times y1 of x. So in that home screen command line, this is basically me typing out the left-hand side of my derivative, my DE. And if I hit enter and have it evaluate, we should find that indeed we get 0. Right? That would be a confirmation that e to the 4x is indeed a solution. If I want to check the other one as well, I ought to be able to go back in here. I'm not sure if I can do it with this. Apparently not. I would have to type this thing all over again and do this with, let me try it here. Do this with y2 instead. So we're going to have a derivative. Oops. We do second derivative y2 of x. Doesn't like that x button very much. y2 of x, comma 2. And then we have minus 8 times second. We have derivative of y2 of x, comma x. That's our first derivative, minus 8 times the first derivative. And then lastly, plus 16 times y2 of x. So again, if I hit enter, we should again see that we get 0. So that is what we're looking for to verify these solutions. This is a very handy little trick, and it should work a little more normally on your handheld calculator on your TI-89. If you have something other than a TI-89, it still works. So anything available to possible, so the Inspire CAS, anything able to do symbolic mathematics should be able to do this sort of thing. You just have to figure out the syntax for your particular calculator. All right, so that was that was the that example here. We have double checked that. And again, what we learned in the previous example was that if e to the 4x is a solution, if e to the 4x is a solution, and x e to the 4x is a solution, then any linear combination of these should also be a solution. For example, here's a specific linear combination, 3 e to the 4x. So this is 3y1 minus 5y2, right? This is a specific combination. And in fact, any general combination such as y equals c1 e to the 4x, excuse me, c1 e to the 4x plus c2 x e to the 4x. This is the sort of general combination, general linear combination that we can make from these two solution functions that we were given. So you can think of this as being a general solution to this differential equation. Why do I think this? Because it is second order, and I should therefore expect to have a general solution that contains two unknown constants. And that is what we have here. So this should be a general solution. So the only thing remaining really is, where did e to the 4x come from? Where did x e to the 4x come from? So that's something we would still have to answer in this section. But this is our general solution. All right, so a little bit then, looking ahead slightly, what we've just been talking about is, by that superposition principle, we are able to create a family of solutions from particular solutions. So we just did that and did a nice job there finding a linear combination of two solutions. I'd like to illustrate one other little point that is important for this section. Here is a different HEQ, homogeneous linear equation. We are again given some solutions for it. Some specific particular solutions for it are 2e to the x, 4e to the x, and e to the 3x. So again, what we just learned is we can make linear combinations out of these and get more general solutions. So there's different ways to do this and different significance here. So I'm going to look at, just for demonstration, imagine initially we make this linear combination. I'm called this somewhat suggestively the less meaningful linear combination. And the idea here is that if y1 and y2 are solutions, then making a linear combination of y1 and y2 is also a solution and is more general. But I claim that this is less meaningful because effectively there's no point in having a 2c1 and a 4c2. These are still just unknown constants. So you call them k1 and k2 instead, but then you've just got k1 e to the x, k2 e to the x. There's no point in that either. You can factor out an e to the x, and you really just have some unknown constant times e to the x. This is more general than just 2e to the x or 4e to the x, but I say this is not a very meaningful linear combination because we don't end up with the sum of two solutions in the end. We only end up with one constant when we're expecting two, and so on. So a more meaningful linear combination would be, let's look at combining y1 and y2. Excuse me, this should say that's a typo. I didn't notice that before. Let's say y1 and y3, or let's say combine y1 and y3. If we do the same linear combination idea with y1 and y3, we get this. And again, we can re-envision or rename C1 to include the 2. We have just a C2 here. And notice that this is a more meaningful, more general, again, that's probably what we mean here, is a more general linear combination, because we cannot combine these into a single term. We now do have a solution here with 2 unknown constants in it, which is what we're expecting for a second order DE. So this is more meaningful. So the question is, why is the first one less meaningful and the second one more meaningful? Or why did the second one end up more meaningful? And the point is, it's because they weren't able to be combined. The first 2 were able to be, so the point is, loosely speaking, y1 and y2 in the original example weren't really all that different from each other. They were both e to the x type solutions. What we needed to get something more meaningful and more general is 2 really different, actually different functions. That is, a type e to the x and a type e to the 3x. So the terminology we use here is that e to the x and e to the 3x are independent. That's also a typo. That should say, my apologies, that should say y1 and y3 are independent, but y1 and y2 are not independent. They are dependent. So the point is that dependent is very similar. Another way of thinking about dependent is constant multiples of each other. So y1 and y2 are really just constant multiples of each other. y2 is 2 y1s, but y3 and y1 are not just multiples of each other. They are actually different, and the term we use here is they are independent of each other. So that's basically it. There's one more little question to test you on this on my open math. And then we do have a little bit of prerequisite material to talk about. I think a lot of people at this stage in math have done this before, but we are going to, so, well, let's see here. As we just discussed, we are interested in determining whether functions are linearly independent of each other or not. So this is often fairly easy to do, especially if you only have a couple of functions. Linearly independent means, are they multiples or not? But if you have more than 2 functions, so for sets of more than 2 functions, it becomes a little trickier to decide whether a set of functions are linearly independent or not. I'll let you take a little look-see here. But it turns out for our work, the way we can test this is by something called the Wronskian. The Wronskian is something from linear algebra. So we're going to borrow a little bit of work from linear algebra here. The Wronskian is basically a determinant of a 3x3 matrix that contains functions, functions and their derivatives, basically. So what I need us to look at here is we want to look at how do you take the determinant, how do you find the determinant of matrices? So a little discussion here. Generally, we will only need 2x2 and 3x3 matrices. So let's take a look here. If you have a 2x2 matrix, let's just say it is A, B, C, D, then the matrix, or excuse me, the determinant is found by, I usually think of it this way, you multiply in this direction, so you get AD, and then you multiply in this direction, you get BC, and you subtract. So for a 2x2 matrix, this is your determinant. Also notationally, determinant is noted by, again, like absolute value bars is like around a matrix. It means to take the determinant. So that is a 2x2 matrix, and I imagine we know how to seen that before, but just a reminder. What happens then in a 3x3? How do we take the determinant of a 3x3 matrix? So imagine a 3x3 matrix is A, B, C, D, E, F, H, I, J, I guess I lost the G. Let's keep it alphabetical. E, F, G, H, I, let's say that. So what would be the determinant of a 3x3 matrix? So there is a little bit of theory behind this, but I'm really just trying to get us the method here. We do the determinant of a 3x3 matrix by something called cofactor expansion. So that is, you can pick any row or any column and basically derive the determinant from that row or column. So let me pick a nice color here. Let's say we do an expansion about the first row. Then the idea is that you start each row. So we're going to start with the A here first. So this becomes, we do A times, and then you imagine crossing out the row and the column that contains the A, and you do the 2x2 determinant of what is left over. So we would do A times E, F, H, I, first part. So once you have done that, I need to get rid of those. We then move over to the, move over to the next element in that row, and we cross out that row and column, and we then have the B. Now it always alternates sign, so this would be minus B, and then we would do, again, the 2x2 determinant of what remains, which would be DF, G, I. And then again, we would need to move over to one more. The next one is the C. We cross out that row and column, and then we do, again, we alternate the sign. So this is plus C again, and we do the 2x2 determinant, D, E, G, H. So that is how we would, again, so now we can then evaluate this, right? We can evaluate this, we can evaluate this. Be careful with your signs. We can evaluate the determinant this way. So what happens is, it actually doesn't matter how you expand. You can use any column or any row to expand to do a cofactor expansion. For example, real quickly, if I had the same matrix, A, B, C, D, E, F, G, H, I can also expand. Let's say I expand about the second column. If I expand about the second column, then I'm going down this way. Yes, going down this column. So this would be, I would start with a B. Now, a little secret here, we would start now with a minus B. So you kind of think of it as the position here. So you're thinking in your mind that the positions go plus, minus, plus, and then minus, plus, minus, plus, minus, and then plus, minus, plus. So now that I'm expanding down this column, this would be starting with a minus B, and then I can alternate as before. So I would do, here's my B, I would then do DF, GI, and then we would then move down our column, and we would do next, we would be doing around the E, which would be like this. So we would have a plus E, and then we would do our product, AC, GI, and then lastly, we would have a minus. So we would have a minus H, and then we would have around the H, we would have ACDF, ACDF. And again, if we do this correctly, either one of these will come out the same determinant number. But again, this little business with the signs is what sometimes trips us up. And again, there is a lot of value in being able to pick a good column or a good row to do cofactor expansion over, because naturally columns and rows with lots of zeros in them are easier to work with. So that's sort of the idea there. All All right, so there are some examples here to try. I should have led you to do, I'm going to squeeze in some 2x2 examples earlier. We will have some 3x3 examples here. So there's a couple of 3x3 to try here. And then a second one. And then a little thinking question about choosing the best row or column to do the expansion over. And then last but not least, here is an example to just find no help, no aid, just find the determinant of a 3x3 matrix. Okay, then the last thing remaining here for you to do in this video is we will be solving some of these, at least in theory, and especially the exercises in the homework can often be solving initial value problems. So there are a couple of examples here to practice solving second order initial value problems. So these questions will step you through the process. So take a look at the first one. And then there's a second one to try. The second one involves some trig functions. So it's the same process, just involving some different functions to try. And that is it. So that will be it for this video today. We will cover the rest of this section in class together. Thank you.